Hello, class. This is the part 2 of the 2 sets of lecture for mass wasting. This is your teacher and lecturer for today, Dr. Sandra Catane. May I just correct my earlier statement regarding the Ginsaogon last slide in the first part of the lecture. The volume was given at 14 to 18 cubic kilometers of rock debris. The correct volume is 14 to 18 million cubic meters. The previous discussion, we were discussing about rainfall-triggered landslides. In the next discussion, we will talk about the triggers of landslides. This time, the trigger is earthquake. Ground shaking due to earthquake activity can facilitate slope failure. The avalanche from the Mount Huascaran in Peru was triggered by the 1970 Ancas earthquake with a magnitude of 7.9. It is considered to be the world's deadliest avalanche with 70,000 casualties. This is the area of the deposition of the Huascaran debris avalanche at the bottom of the valley. The materials originated from the high peak of Mount Huascaran and descended down the valley, devastating the people and the villages at the base of the mountain range. The other example is the Northridge earthquake in California in 1994, where many landslides were induced by that earthquake. The more recent example in the Philippines is the Batu landslide in Cotabato. The October 16, 2019 magnitude 6.4 Cotabato earthquake triggered the landslides. The photo of that landslide was shown in the first part of the lecture. Moving on, the September 6 Hokkaido Ibori Tubo earthquake with a magnitude of 6.6 triggered hundreds of landslides over the island of Hokkaido. Well, in fact, there were about 800 individual landslide events that were counted. Scientists claim that the island was primed for landslides when heavy rains from Typhoon Jebi, the most powerful storm to strike Japan for 25 years, saturated the soil. And because of the saturation of the soil, it was easier for the earthquake to loosen up these already saturated materials and produce this numerous landslide in Hokkaido. The Batu landslide in Cotabato province is an earth flow, and probably the materials at that time prior to the earthquake were already saturated by rainfall, and therefore it was easier to dislodge the soil materials in this ridge because they are already weak and saturated with water. How human activities increase the frequency of earthquakes, rather landslides. Deforestation, cultivation, and construction can increase the frequency. Construction or earthworks by altering the shape of the slope over steepening of the slopes. Road cuts, blasting, and quarrying activities, which is quite common open pit mining operations, can trigger landslides. Vibrations from machinery or traffic. Buildings and structures built on naturally unstable slope, and this is related to the additional load on the slope that could trigger a landslide. Irrigation, watering of lawn, using septic tank for sewage disposal, these seemingly benign activities can also trigger landslides. In shallow soils, the removal of deep-rooted vegetation that binds the soil to the bedrock can be a trigger. Agricultural or forestry activities such as logging, urbanization, which change the amount of water infiltrating the soil. Human impact on mass wasting. There are several ways human activity can increase the risk of landslides. Slopes oversteepening produce more level surfaces in this example can lead to slope instability and failure. The concrete covered wall gave way because the slope is too steep to be stable. Regardless whether there is a concrete wall cover or not, the slope is unstable. A highway in the US is perennially blocked by a landslide debris. Often, the debris from this moving landslide block the highway, and the earthwork activities, by removing the debris from the highway, they can open the road again. But after some time, when the landslide moves, it blocks the highway again. Addition of water through irrigation, septic tank systems, artificial ponds or leaky ground pools can loosen up slope material and adds weight, promoting slope failure. The vegetation concentrates surface runoff and enhances erosion, resulting to steeper slopes, reduced interception, and evaporation increases the amount of water in the ground. Meaning, if you're going to pave all the areas in your surroundings, then the infiltration of water is reduced. And therefore, it can impede water flow that can result to landsliding. How to live with landslides? About 20-25 lives are lost as a result of landslides in the US every year. In the Philippines, we experience landslide most of the time, especially during the rainy season. Many landslides are associated with tropical cyclones and monsoon rains. The casualty is probably the same rains with the US, except for massive single event landslides, which resulted to more than 1,000 deaths. Example of that is the Ginsaogan landslides, which claimed more than 1,000 lives. The more recent landslide in the Philippines is the Naga landslide in Cebu Island. This landslide occurred on September 20, 2008, and the landslide generated 27 million cubic meters of debris. The run-out distance, or the distance traveled by the landslide, is 1.34 kilometers, and there were 134 people died because of this landslide. There is no apparent trigger, earthquake or rainfall, for this landslide, but progressive weakening of oversteepened slopes due to quarrying and mining may have been one of the causes. This diagram shows the success of Japan in reducing the damage brought about by landslides. The data is from 1938 to 1981. If you look at the trend from 1938 to 1958, they incur a lot of of damages and casualties related to landslides. But by 1959 or 1958, they instituted land use and management controls in order to reduce or mitigate the effect of landslides. The regulations include restrictions on where to build, which structure can be built in landslide-prone areas, and prescribed methods which can control mass wasting. It also includes warning system, education of the population on how to respond to those warnings. If we look at year 1981, there's 1978 to 1981, there's virtually very little damage or deaths related to landslides. How do we recognize or how do we know if the landslide occurred or will not occur? There are some parameters or things that can be observed in the area. If there are scars or barren rocks or lack of vegetation in rock slopes, then that could be a sign that a landslide occurred in that site. It can also be disrupted topography, and this is quite apparent in topographic maps. Probably historical records of past avalanche is available, or in volcanic areas, record of past volcanic activity, for example, debris avalanche, can give you an idea if there is a possibility that it will occur again, because the rule of the thumb is that where you have present landslide, it's probably because they are already occurring in the past. And of course, if you observe tilted vegetation, it could be an indication of a creep. Other indicators are cracks in the driveways, garage floors, or freestanding brick, or concrete walls, buildings, crack on the walls and ceilings. These are possible signs of landslides, but not always. What can be done to prevent or correct landslides? Identify the potential hazard, conduct or map unstable areas, consult a geologist, avoid landslide-prone areas. You can do zoning. You can generate also hazard maps so that you can identify the hazardous areas or how susceptible the area is susceptible to landslides. You can do engineering measures such as slope reduction and revegetation. Use retention structures, vertical piles on the toe of landslides. You can use buttress or gabions or other types of retaining walls. Rock bolts can stabilize rocky slopes, but these engineering interventions are quite expensive, and the cheapest would be the number one. So the first thing that has to be done in an area is for a geologist to check or to map or identify the hazards related to landslides. Removing fluid is also a solution, and as you know, water can induce landslide. That's why removal of fluid or water can be helpful. Or maybe you reconstitute the materials on the slope by using chemical treatment. Landslide hazard maps normally indicate the possibility of landslides throughout a given area. It can be a simple map that uses locations of old landslides to indicate potential instability, or complex as a quantitative map incorporating the probabilities based on variables including rainfall thresholds, slope angle, soil type, levels of earthquake shaking, and so forth and so on. An ideal landslide hazard map shows not only the chances that the landslide may form in a particular place, but also the chance that it may travel downslope at a given distance. So the prediction of the run out or the distance travel that the landslide can travel is also very important. Landslide hazard maps. Several kinds of maps are used to depict dangers from landslides. Landslide inventory map, such like this, it shows the location of past landslides. And landslide susceptibility map, it describes the relative likelihood of future landsliding based solely on intrinsic properties of a locality or site prior to failure. From the landslide inventory, rock and soil strength and steepness of the slopes are three of the more important site factors that determine susceptibility. Landslide hazard maps indicate the possibility of landslides occurring throughout a given area. Landslide risk map show landslide potential along with the expected losses to life and property should a landslide occur. Risk maps combine the probability information from a landslide hazard map with an analysis of all the possible consequences like property damage, casualties, loss of service. This is an example of a landslide susceptibility map. This is a map of California showing the incidence and susceptibility at the same time of areas in California. This is a map where you have more details of a particular area. It shows the slope. This landslide susceptibility is overlain on a Google map in this particular example. Mitigation measures. Mitigation measures should include slope stabilization techniques. In this particular example, techniques of keeping the water out. Water is bad for the slope, so it's better to take it out or divert it elsewhere. Drains and trenches like this keep water from infiltrating on top of the slump. Another short-term precaution against further water input and erosion is using this special type of textile called geotextiles. Or you can also do revegetation and at the same time improve the drainage of the slope by installing drains and pipes and canals. This is a combination of revegetation and drainage. Further, this slope stabilization utilizes revegetation as a technique. This is the bank that has been undercut and eroded by a stream. They tried to restore this riverbank by planting vegetation, and this is what happened after the banks of this river was stabilized using the vegetation. In this particular case, they use a combination of geotextiles and vegetation to stabilize the slope. Slope stabilization using retaining structures. An example of a retaining structure is this wall here. It's a retaining wall. It's not the same as a riprap, but it is an engineered structure with a specific design. It has this cantilever which helps in preventing movement of materials down the slope. It has also these whip holes or drainage that allows water to drain. It is much thinner stem and utilize weight of the backfill soil to provide most of the resistance to sliding and overturning. This is a graded slope with surface drains. Graded means the slope was cut in such a way that the materials become more stable on that particular angle. Further, we have more retaining structures shown in the pictures. We have the wire mesh protecting rock falls from the slope, protecting the motorists passing along this highway. We also have geogrids that holds unconsolidated material in place so that it will be more stable on a slope. We have also wire baskets filled with rocks, or sometimes they call this as gabions. Example of slope stabilization technology, ground anchoring. This is a rock bolt. This is the way they install the rock bolts, by drilling into the rocks, putting pressure monitors or piezometers. They also put rock bolts across planes of weaknesses. Rock bolts are also used to retain unstable rocks in tunnels, road cut slopes, and road tunnels, and in roofs of underground mines. In this diagram, it shows how effective a rock bolt is in anchoring the overhang of a tunnel. And also here, these are rock bolts strengthening this wall so that it can support material on the slope. There are also shelters that basically protects motorists when passing in a landslide prone area or rockfall area. In some landslides or avalanches, avalanche prone areas, slope stabilization is impractical due to the scale of unstable slopes. This is particularly true for roads in the mountainous areas. In this case, shelters or sheds are used to divert landslides from the road and people on it. As you can see, there are tires, old tires on top of this shed. The purpose of these rock tires, old tires, is to absorb shock from falling debris. Along Marcos Highway, a few kilometers from Baguio City, are engineering structures meant to address landslide hazards. It was built during the reign of President Ferdinand Marcos in the early 80s. The total cost of this slope stabilization project was 70 million at that time, excluding the yearly maintenance. The flyover here that you can see is not a normal elevated highway, as it can allow delivery of water and debris underneath. Sediments and debris are transported by the Tuba River, especially during the rainy season. The skyway or flyover was built on piles and can accommodate some movements and displacement along the Tuba fault. The rock sheds protect motorists from rockfalls. It is constructed such that it can sustain impact from rockfalls. Rock fences are meant to catch small rockfalls. The shotcrete here is used to protect slope surfaces from erosion, or used as a supporting structure combined with ground anchors or soil nails to stabilize the slope. The last slide is a technique or specialist field in geotechnical engineering. They call it as bioengineering. In bioengineering, their favorite vegetation or grass is the vetiver. And this is a showcase of installation of vetiver grass in Tagaytay Highlands for slope stability. In March 2002, they started to grade the slope and plant vetiver. After a few months, the vetiver started to grow, and in July 2003, they have already grown to several inches, several centimeters, and after a year, this is how it looks like. What is a vetiver? This is the vetiver. Vetiver is a perennial clump grass with sterile seeds usually used for soil and water conservation. The grass forms a dense, permanent hedge that prevents soil erosion, soil loss from runoff, thereby improving soil fertility and water quality. The World Bank has been actively promoting vetiver as a grass that would help conserve soil or soil erosion, water, runoff retention, and slope stabilization. Vetiver roots can grow up to 5 meters. In this case, it's about 3 meters. The leaves can capture CO2 and can be used for slope stabilization and erosion control. The living plant is used to conserve soil and water. The roots for treatment of contaminated land and for slope retention. This ends the lecture on mass wasting part 2. Thank you for watching, and don't forget the warning.